In this video, we're going to be modeling a simple dipole antenna. So, now the dipole antenna, you can go through this. It's the simplest form of antenna. The radiation pattern of the half wave is zero along the antenna's axis and maximum perpendicular to the conductor DM, and you'll also see this from the simulation. Now, the aim of this lecture is to model a dipole antenna in CST Studio. So let's get on with it. Now open a new project. So as usual, go to 3D simulation. You've opened your CST Studio, and then you go to 3D simulation and go to high frequency as the problem type and frequency domain solver. Now when you open the high frequency um, model, the default is time domain solver. So you go to solver setup and change it to frequency domain solver, and change the units from millimeter to unit of length to millimeter and unit of frequency to gigahertz. Now in the 2022 version, this already comes with millimeter and gigahertz. I think in previous versions, this should be meter and gigahertz. So make sure to change this to millimeter and gigahertz. So that's already the default. Now apply open boundary conditions in all directions. Now this is going to be applied to the background material. So I think that is going to be defined later, but we'll get there. So let's go. Should I do that later? Oh, yeah, I'll just apply it. But then just know that it's applied to the boundary condition. So it's open, add space, but we don't really need the extra space. So I would apply open boundary condition to all directions, just like we did for the capacitor. Then in the simulation tab, click on discrete port. So simulation tab, then click on discrete port. And what do we do? And so we're trying to match this. So it's one, and then okay, now this is quite small for me to see. I would expand it a bit. If I can get a handle on this. Okay, so this is 0 0, this is 1, and this is -1, and I think that's 0 and 0. Yes. Oh, that's really small. Maybe if I can make it bigger. Yes, 0 0 1 and -1. Yes, you could preview it, and you have this your discrete port, which is the source in this problem. And okay, monitor voltage output and input. I don't know if that was already ticked, so I'm going to check it. So you've defined a port, and then so that's a discrete port, so you could always edit it going back, so it's already checked. So to edit it, you just double click, and then the define port command, then you double click, and then you see you could edit the values after you've already defined it. So close. Now over to the next. Now create a variable with name length, and should I? Yes. So go to parameter list, and then click on parameter list and new parameter length, and then set the value to 50, which is 50 millimeters. And for initial value, then create two cylinders adjacent to the discrete port. So with these dimensions, I'm going to make them a bit bigger. The box is a bit bigger, so I could see the dimensions. Yes. So to create the cylinders, you go to model, and then one of the primitive shapes is cylinder. So create cylinder and then escape. And now for the first one, we just copy the dimensions here. So 0 0.1, 0, and the orientation, be sure to change the orientation to Y. So this is 0 0.1, and then this becomes length, half of the length, and this is 1. So we could go ahead and preview that. So this is what we have. Yes. And yes, perfect electric conductor. And then for the second cylinder, click on cylinder, escape, and we fill it in with this. So orientation Y 0.1. And what else do we have? -1 and minus half of the length, and material is spec. Yes. So that gives the other part of the antenna, which is the bottom side. Now over to the next slide. Increase the surrounding space by changing the background properties. Now remember the open boundary conditions we applied initially. It's applied to the background space. So increase the background space. So you could either do it from here or from simulation. So now we copy this to match this. So normal 40, 40. I could just apply to all directions. Okay, yes, it does. And then this is 20 and 20. So 40, 40, 20, 20, 40, 40. So apply. Now I think the bounding box is still turned. Okay, it's not turned on. I could turn off my, let me make this a bit small. Okay. Oh, I don't like seeing the working plane. But I could turn on the bounding box, visibility, bounding box. Yes. So this is the surrounding. And then you could see at the middle the antenna, quite small, but yeah. So we're done with that. And then in the simulation tab on frequency, insert 1 and 3 gigahertz for the lower and upper bound. So we want to define the frequency range that we're interested in. So simulation tab, then frequency, so 1 gigahertz and 3 gigahertz. And okay, that's that. Then in the field simulation, in the simulation tab, click on field monitor. So we want to monitor the field at 2 gigahertz, the electric field and magnetic field vectors at electric field, magnetic field, and also the far field at 2 gigahertz. So field monitor, the type of field monitor we need, electric field, it's already at 2 gigahertz, but if it's not, you select 2, and then we want frequency, so 2 gigahertz, and then we click OK. I think if we click apply, it shows yes. So if you click apply, it already appears here. Then you can change it to your H field, and you click apply. You have H field monitor, and then far field. You click apply. You could also monitor different things, but then we're only interested in the E field, H field, and the far field at 2 gigahertz. So okay, and I think a monitor with this name already exists. Do you wish to replace it? No. So I will just have to cancel that, because if you click OK, it tries to create a second monitor for far field. So I cancel out since I already have all of the fields that I am interested in. Now run the simulation, disable adaptive meshing. So I go to solver. So remember, you could either do it from here or you go to home and then you click on this, the top button. This has 2 buttons, but you click on the top one. So either of the places. So I click from here and then general purpose, tetrahedral, all ports, and then you just leave the settings as it is, but then you turn off the adaptive tetrahedral mesh refinement, and then you start. And this should be done very soon. So that's that. Now let's see the E field at 2 gigahertz. So if you should go to your 2D stroke 3D results and you go to E field, then you can look at E field at 2 gigahertz. So looking at the front view, this is what we have, but then we are viewing the whole 3D. We are viewing the whole 3D field, so we can just decide to look at the field on a particular plane, and then you go to sectional view and then fields on plane, and you have that it just views the field profile for this plane. And let's see, and compare with the image we have here, you see that we have the same field profile for the E field and then for the H field, and this is the YZ plane, and then for the H field we have this. It has only normal components. Okay, something you can see from this is that it has just tangential components, the E field. So if you should look at the YX direction, you see that it doesn't have any. The E field at 2 gigahertz does not have a normal component, so the field is just tangential to this plane, so your YZ plane. That's for the electric field. Then for your magnetic field, you have only normal components. Now let's look at another, because you don't see any arrows on this plane. Now let's look at another. So we have cross section A, but I'm going to turn off cross section A and view cross section B. So when you look at cross section B, I could also try to adjust this for better viewing, or just click on color ramp and smart scaling. Then it's now too bold, but then I could adjust this for, yes. So I'm just clicking and holding on the color bar, the numbers on the color bar, and moving them up and down to improve the, not visibility, but the arrows, to increase or decrease the arrow size for a better view. So it's the H field at 2 gigahertz. It's similar to this, so we did everything correctly. Now lastly, or maybe not lastly, I think we still have some slides. So in the 2D and 3D results, 2D and 3D results, the field distributions could be observed. And yes, then the last field monitor we put was the far field. So when you click on this, you have this. So the field value is maximum at the horizontal axis and minimum. You could see it's minimum in this axis, just as was described in the either first or second slide. So this is what we have. So far everything is good. And then we look at the 1D result and S parameter to see this plot. So you go to 1D result and then S parameter, so S11. So this is what you have at about almost 2.8 gigahertz. You have your rejection. So your transmission, your S parameter, this is of minus 20 decibels. And now use appropriate symmetry planes to reduce the computational size, then enable the adaptive mesh refinement. Try to calculate the length such that the minimum point of S11 curve is located at 2 gigahertz. For this purpose, once use parameter sweep of the CST studio and then optimization. So applying the appropriate symmetry planes, I think maybe I'll just mention that. So again, to get the appropriate symmetry plane, you have to look at the geometric symmetry and also the, would I say, boundary condition symmetry, the field symmetry. You look at the field symmetry and also the geometric symmetry. Now from the geometric symmetry, we could see that you have symmetry in 3 planes. So just like with the capacitor example that we did in tutorial 1. So you see that you have 3 symmetry planes. Now to determine the proper symmetry, so to apply your symmetry condition, you go to boundaries and then symmetry planes. So to apply the proper symmetry condition, whether it's Et is equal to 0 or H is equal to 0, you have to observe the field. So for this example, you see that for the H field, okay, this is the E field. The E field on, you have only normal components of the E field on this plane. So on the YZ, no, not on the YZ plane. Yes, on the YZ plane, you have only normal components of the E field. Let's see. And then the H field, you have just tangential components. So Hn is equal to 0, which implies in CSC Ht is equal to 0. So if you were to apply to the Oh, sorry, that's XZ plane. Sorry, that's on the XZ plane. How do I view this? 8. Yes. So this is the XZ plane, and you have only tangential magnetic component. So that's H n is equal to 0, which corresponds to H is equal to 0 on the XZ plane. Now, if you should look at the, go to 2D, 3D plots, and then let's look at the normal, let's say X. So this would give you the XZ plane. Now your E field on the, where is it? Yes, your E field on the XZ plane is tangential, purely tangential, which means that your En is equal to 0, and this corresponds to Ht being equal to 0. So your tangential magnetic field being equal to 0. Now you can also see that by observing the magnetic field. You see that it has only normal components. So the components point either into or outside of the screen. So with that you could, and then in the third axis, that is this, which is the XY. So normal is Z. You also have purely normal magnetic field. So Hn is equal to Ht is equal to 0 also on this plane. So when you apply this, you simplify the computation domain, and yeah, so you reduce the amount of time you use to solve the problem. Now I'm going to skip that. You try that on your own. Then now try to change the length such that the minimum point of the S11 curve is at 2 gigahertz. So currently we have that the S11 curve, the minimum is at about maybe 2 point, almost 2.8 gigahertz. Now the goal is to kind of optimize, not kind of, it's to optimize the length of the pole such that you have this minimum at 2 gigahertz. Now you could do this manually, which the first part of the task suggests. For this purpose, use parameter sweep. So you could sweep through different lengths to see at which for which length you have that the minimum is 2 gigahertz, or you could use the optimization module in CST for that purpose. So the first one is doing a parameter sweep. So to do a parameter sweep, you go to simulation, and then on this, I think if this is stretched out, you see that it shows parameter sweep. So the first of these buttons is parameter sweep, and then you go and add a new sequence. Then under the sequence, you add new parameter. So we want to sweep over the length, a linear sweep, and then we are going from 50 to 80 millimeters. And then how many samples do we need? 7. Hopefully this doesn't take time to solve. So once we are done with that, we can click OK. So we are looking at 7 lengths: 50, 55, 60, up till 80. So you could start that. Hopefully it doesn't take time, but I'm going to pause anyway. So we currently have a result. So just delete the current results and let that run. Okay, it's done with the sweep. And as you can see, you have different minimum for different lengths. So for L is equal to 80, you have the minimum at about maybe 1 point. I could also view this by going to minimum and then moving. So what I did was, you could either include a marker, axis marker, at a particular frequency. So let's say maybe 2 gigahertz, and then you have a marker and you can slide this marker around. So this is at 1.7 gigahertz. Then for length of 75 millimeters, you have it at 1.8, and for a length of almost 70 millimeters, you have it at 2.01 gigahertz. So this is one way. This is manual, and then you could maybe do a different sweep for maybe let's say 769 to 71 to see how much it shifts, but then that is not very efficient. And a second way to do it is using the optimizer. So it optimizes the minimum to be at 2 gigahertz, optimizes the length such that the minimum S parameter becomes is at 2 gigahertz. So let's look at that. So we looked at the, what's this? Oh boy. It's okay. Yes. So we use this parameter sweep, but now we want to use this. But then before that, we have to, I think, yes, we would have to get the result that we want to optimize. So now we want the minimum of the we want the minimum of this parameter to be at 2 gigahertz. Now we go to result template. So in post processing, you go to result templates, and there's really no one way to do this. So I would show you maybe just two ways of doing this. So I would follow this first, and then I would do a second way. So for optimization, first open the result templates tool, and then 1D result, and then 0D or 1D result from 1D result. So because your S parameter is a 1D result, now what we want is then evaluate the S11 parameter at 2 gigahertz. So what we want is the Y at a given X. So we go Y at given X. So Y is the S11 parameter and X is 2 your frequency. So we want to calculate Y at 2 gigahertz. So what we want is the magnitude, and then okay, we could also use the magnitude in dB, and then okay, and then we can evaluate this all runs, and the value is 0.69. Now this scale is in dB. We could also change it. Now when you want to change the axis of the plot, you go to this and 1D plot tab, and then you can have it in linear scale. So you in linear scale you have, I mean, from 0.1 to 1, and then in dB you have 0 to -20, and then I think you could also view it differently. Let's see, phase linear. Okay, I think those are the ones. So you could also as well make it in decibels, then you would have -20. Maybe I would add that, should I? Yes, I will. No, it's not important. Okay, it's not important. So I'll just leave it. So I'll change this to a linear scale. So you see that it's 0.69. That is for which of them? Let's see. So I go to table 0D result, and yes. So for a length of 65 millimeters, you have that the S parameter at 2 gigahertz is 65. It's 0.57, which you can confirm from here. So at 2 gigahertz, you could right click on this. Okay, maybe a bit slower. So if I want to precisely fix this, because I could slide it, but if I want to precisely fix it, I'd right click and then go on properties, and then just click 2 gigahertz. Now I see the value at 60 for a length of 65. That's 0.576, which is what you have here. Now then since we are done with that, we in the home tab, either the home tab or simulation tab, you click on optimizer. Yes, so optimizer, and then you could select the different optimization algorithm. I think which one is easier, trust region network. Okay, you could read up on the different algorithms yourselves. So what we want to optimize is the length, which is the only parametric variable we have, and yes, we change the minimum to 50. I think this should be 50 or 60. Is it 60? Yes, 60. And the maximum to 90. So this is just the range of length that it would try to optimize in this length range. And then, so minimize this again. I'll make it smaller, not minimize. Then expand this. Then you go to goals. So we want to add a new goal, and the goal is, now we navigate, we click on this and then navigate to the result that we evaluated. So what we evaluated was S11 at 0D, Y at given X. So this is what we want to optimize, the S parameter at a particular X, which is 2 gigahertz. Now, what do we want from this? We want it to be less than 0.1. And yes, that's a difference. Wait, just leave the other things and then click on OK. So we have one goal. So this is just a um, single objective optimization problem. And then after this, we go on to we've already added new goal and this, and then we can now start the optimization. So I'll start the optimization, and then once it's done running, I'll pause and I'll be back when it's done running. Okay, the optimization is done, and then you see the result here. The length, the optimal length for which you have the transmission to be less than 0.1 is 70.633. So that's the optimal length for which you have the. So I'll just go ahead and apply this and close out, and then you see if I should go to view the S parameter and I view it for just the current length. Okay, it's still showing results for all of them. So I think I have to run it once more. So I've already applied the optimized length. Now I just have to run it once more to update the results. And voila, we have that the minimum. Now this is dB scale. So the minimum is at 2 gigahertz. So we have that. Now that's one way of running the optimization. Now one may ask, why did we choose zero point 0.1? I mean, if you look at the optimization, you see that the value is still not less than zero point 0.1. So it's like we set zero point 0.1 is a method of optimization. We set zero point 0.1 as kind of an ideal solution, less than zero point 0.1 as an ideal solution. And then we find the value, so the value of length with the minimum error from this ideal solution that we place. Now that is one way of running the optimization. A different way of running the optimization is going to result templates, and then instead of um, getting the y at a particular x, you could also still general 1D. You could also define a different variable, a different object. Is it a variable or an objective? Maybe function value, s value. Um, why is it not? Where is it pop up? Okay, now it's here. Now initially we define y at a given x, but then we could also define the global minimum, the global y minimum as a variable. So if we should define the global y minimum as a variable, then we check the magnitude, and this is what we have, and then you evaluate. So this is what we have as the global y minimum. Now in your optimization, which is in simulation optimization, I'm going to delete this goal now. I'm going to delete it just because I mean, we don't need to define two goals because they are kind of exactly the same thing. So I would delete this, right click. Okay, no, not right click. Remove. Yes, remove. Remove this goal. Now what you can do is setting still remains the same, 60 to 90. That's going from the length values to check it's from 60 to 90, and then you go to goals and then add new goals. Now we want the y, the global y minimum. Oh, sorry, not this. I made a mistake. So not the global y minimum. We want the, so back to post processing, result templates. Now instead of the global y minimum, we want the x. So the frequency at the minimum, at the global y minimum to be 2 gigahertz. So not the global y minimum, but the x at the global y minimum. So the x at the global y minimum of this curve, that's what we want to define. So this is what we have. Currently, it's 2 gigahertz. Where is it? X at global y. Sorry, this is maximum. X at global y minimum. Yes. So currently it's 2 gigahertz because it's already optimized. for this, but then I'm going to change the value again and try optimizing it again. So we have the x at the global y minimum. Yes, I got that right this time. So you go to optimize, but then before I go to optimize, I want to change the value because then it won't do anything. So I change it to 65 and see if we get the same result. Okay, before that, take note of this value 70.63. So 65. So I'm kind of resetting everything again and trying the optimization again. And I go to, so I've changed the variable. So now I need to update. So you press F7 to update the parameters, or you go to home and then you'll see on edit, you see parameter, then you're supposed to see parameter, yes, parameter update. So it's either you press 7 or go to home, click your home tab and then come to parameter update. Now the display should be different depending on how wide your screen is. It's because I minimize it, that's why you have everything kind of hidden. If I should expand this, then you see it's already here without having to click so much. Now to the optimization, now we have exactly the same range for the length, and then I have to remove this because it's wrong. So I remove this and then I go to add new goal. And then what I want is that the X at the global minimum. So X is your frequency at the global minimum. Now I want this to be equal to 2 gigahertz. Now this removes the burden of having to know, okay, zero point 0.1, because if zero point 0.1 just seemed arbitrary. So um, instead we could just specify a specific value, a precise value. So we want the minimum transmission to occur at 2 gigahertz. So that's the X, which is the frequency at the lowest S value, to be at 2 gigahertz, and then that will become a new goal function, and then we can start the simulation. So the optimization, I'll pause and then come back once it's done. Okay, the optimization is done, and then the solution we have is 7.475. I think the previous solution was 70.3 something. But then let's look at the S parameter. And this could be because of, I mean, the values are not equal. Yeah, maybe a bit different, but then this could be because of the mesh refinement. So let's see. 70.475. So I have to run this again with the new um value. No, not the optimization. Yes. Run this again and then see the minimum S parameter. So S11 and move to minimum and linear. Yes. So this is what we have as our solution. So I mean it's 2.002, but then you could gigahertz, but then you could also change this. Now this is just kind of a demonstration that you could define your optimization problem in kind of slightly different ways, but then arrive at the same result. Now this is 2.002, and you could change the 2.002 gigahertz. That's where you have the minimum. You could change some things in your optimization. So when you define your goals, you could edit this, and then you have the weight and the difference coming not here. You could also use your difference squared, but there's something, some of goals, and I can't find that now. There should be a place for you to be able to um, define the accuracy. Okay, maybe it's not here, but generally, if you should increase the number of meshes, make your mesh finding more accurate, your results would be. So yes, I can't find that here. Okay, but yeah, that was just a demonstration of how you could define your optimization problem in two different ways. Initially, we looked at setting the a kind of ideal solution, right? Which was zero point 0.1, and we saw that it still wasn't less than zero point 0.1, but zero point 0.1 was kind of an ideal solution. and then trying to get the length for which you have your S value as the minimum distance between your ideal solution and the solution that you have. If that makes sense. And then the second way is just defining you just want the minimum, whatsoever it is, whether it's 0.1, 0.5, 0.8, you just want the minimum of the curve to be at at 2 gigahertz. So yes, I think that's that for this. And then you observe that this is the S parameter 0.133. And then from optimization, we have that we actually have a lower S parameter, which is 0.1381. But then with final mesh, you would have that the minimum would be exactly at 2 gigahertz. So that's that. And then remove the symmetry planes and add a brick to the back of the antenna and observe the radiation pattern. So that's the last part of it. And then all we just need to do is to add a brick. Now we go to modeling. Now in 2022, this is grayed out. And if this is grayed out, you can't select it. Now you either click on 3D. So this is for 2022, or in previous versions, you just click on component, and then this becomes active again. So switching between results, it's grayed out, but then you click on your components or 3D, and then you have access now to the modeling tab. So escape. So this is just a simple break with minus 80, 80, minus 80, minus 6. Could preview it, and then where is it? Yeah. So just a perfect electric conductor at the back of the antenna, and deleting all other results. And yes, what do we have? Mm, yeah, that's all. And then we just run the simulation again. Hopefully I didn't miss anything. Yes, and that's done. Now you could look at the E field, and then but then that's not really interesting to see. What is interesting to see is the radiation pattern, which is the far field. Now what you see is that the effect of putting now for the far field, you could also show the structure by clicking here. So you see the brick wall that you included. Now compare this to what you had initially. You see that the radiation was kind of not exactly equal around all the about the y-axis, but then with the addition of this brick wall, you see that it's more focused just in one direction. So the brick wall actually changes the radiation field pattern. Now this is at 2 gigahertz because yeah, of course we optimized to 2 gigahertz. It shifted a bit, but yeah, that's not much of a problem. So yes, that's it for this tutorial. I hope you learned a thing or two. So how does the radiation pattern change? You see that the radiation pattern became concentrated just in one direction, which is the z direction, perpendicular to the perfect electric conductor. So that's it for this video, and maybe see you some other time.